All right, good afternoon, everybody. Let's get started. So welcome to 6004. This week, we're going to switch gears and start with a new topic, operating systems. Now, operating systems is a big topic. We actually have a course that's dedicated to it in much more depth. That's 6033. And so what we're going to see in this and the next lecture is essentially an introduction to operating systems. We're also going to focus on what is the interaction between hardware and software that happens in operating systems. So there are some changes that we need to make to processors to support operating systems efficiently. And we'll see over the course of the next two lectures that those changes are what makes our machines really useful. So let's start with where we're right now. So in 6004, so far, we've seen hardware that can run a single program, right? So you've been building a processor in Lab 6. Last week, we covered the memory hierarchy. So there's main memory. There are also caches. But you have all this hardware, right? Both processor, memory, I/O devices, disk drives, network cards, displays, keyboards, a lot of other things. And this hardware, and in particular this processor, is executing a single program. And this program has complete access to all the hardware resources. So remember back to lecture 4, for example, we looked at MMIO, memory mapped I/O, and you saw how by writing to some special memory address, you could actually make the display output things, right? Or you could make the keyboard, you could read the contents of the keyboard, what key was currently pressed. This is not at all how most systems work, right? So, in a little bit more detail, what we've seen is this interface between hardware and software, which we call the ISA, the instruction set architecture. We've seen RISC-V. There are many others. There's x86, which you have in your laptops, in servers. There's ARM, which is pervasive in cell phones and smaller systems. But we've only seen this ISA, right? This interface between hardware and software. Now, this is not really the common case in system design. You don't write programs that have direct access to hardware, and your systems are not running a single program at a time. You already know this because in your laptop or in any of your machines, you're typically running multiple programs, and all these programs are running on the same machine. They're sharing the hardware. Right? You can start an application, different applications, and have them all execute at the same time. Moreover, these programs that you write do not have direct access to hardware resources. Right? When you write a Python program, you don't write to the display directly. You don't write. You write to standard output or you call a print function or some other language-specific way that's a little bit higher level than writing characters to a particular address in memory. Right? So these programs are not directly interfacing with hardware. Instead, there is what we call an operating system in between programs and hardware. So this operating system is controlling how these programs share the underlying hardware and what each of these programs can do. Only the operating system has unrestricted access to hardware. In other words, the interface between the operating system and hardware is the ISA. And we have a different interface between programs and the operating system, which we call the Application Binary Interface, or ABI. So now we have two different interfaces here. Right? Programs are not directly accessing hardware. They're a little bit more abstracted. So before we dive into the details of operating systems, this figure is a little bit imprecise. And to make it precise, I need to introduce a new concept, that is the concept of a process and the difference between a process and a program. In this slide, we have multiple programs that are running and sharing the machine. But really, when we are talking about operating systems, and in general from now on, I want to make the distinction between a program and a process. So a program is just a collection of instructions. It's just the code. Whereas a process is a running program. It's an instance of a program that's currently being executed. This is just like, in Python you have classes, which is just the code, and then you have objects, which is an instance of a class, right? So it's the same concept. You have an instance of a program that is being executed, and that means that you have both the code, but also you have some state. And that is both processor state, like registers, like the memory that this process is currently using, and also some other resources. For example, this process might be writing to files. And so it will have some files open and some state. The operating system needs to track some state associated to those files. So the other change that you see between this picture and the one in the previous slide is that all of these are processes. They're running programs. And then we have the operating system kernel instead of just saying the operating system at the bottom. And the operating system kernel is just a process that has special privileges that can do things that these normal processes cannot. Now, we differentiate between the operating system and the operating system kernel because an operating system, generally, we refer to as Windows or Linux or Mac OS. When we talk about the whole operating system, this typically includes other programs that make the machine useful. Things like text editors or web browsers or window managers or other utilities. Those actually are not part of the operating system kernels. Those are processes, or those are programs that will run as normal processes. Right? So when you're running a text editor, just because it's part of the operating system, it's part of sort of the set of programs that make your machine useful, doesn't mean that it's going to be running in kernel mode or is going to have special privileges. It's just another application. But the kernel is this special process that is going to directly talk to the machine, that is going to directly talk to hardware. Okay, so the reason we have an operating system is because we get three key benefits. Operating systems really have to do only three things. Okay? The first one is protection. So you're going to have multiple processes here that are all going to be sharing the machine. And those processes might be malicious, might be buggy, there might be mistakes there, and so you would like to isolate them. Right? It would be really bad if we had the ability for a single process to take control over the entire machine or to start reading data from other processes. Right? And so the first and most basic function of an operating system is that it is going to isolate each process and give it its own separate set of resources, and then it's going to provide some guarantees that what's going on in one process is not going to be visible to other processes. Okay, so that's the most basic function. But then we also have abstraction. And abstraction is also really important. What I mean by this is that the operating system abstracts all the details of the underlying hardware. And this is really crucial because we have thousands of types of devices. Right? We have just, for example, let's think about hard drives. You have flash hard drives. You have spinning hard drives, like we saw last week. They're completely different technologies, but there are thousands of manufacturers for each type of drive, different models, right? They all follow slightly different commands. They have slightly different ways of being controlled by software. And so imagine if every time you had to write an application, you had to issue raw commands to the hard drive every time you wanted to write something, right? And wanted to have some storage that lived beyond the life of your program. That would be insane. Nothing would ever work. So instead, what the operating system kernel is doing is it's abstracting these underlying I/O devices into higher level interfaces. So for example, instead of exposing a disk, it's exposing a file system where you can create files, you can read files, you can write them, update them, and so on. Right? And so that makes it easier to write processes that do useful things. Finally, the operating system is also managing all the resources and essentially controlling how all these different processes get access to the underlying hardware resources. For example, if you have more processes than you have CPUs, which is a very common case, we will have to decide which process is scheduled in which CPU at which time, right? Which of these gets the CPU at its particular time? How much memory can they get? How much disk space can they get, right? And if they try to get more than what they have, what can we do about it, right? How can we prevent them from taking over all our resources? Okay, so at a high level, in this slide we're going to see the three major things that operating systems do. It's just three mechanisms. And then over the next two lectures, we'll dive into these mechanisms in detail. The first thing that the operating system kernel provides is what we call a private address space to each process. So each process is given some amount of memory, right? You have main memory, but the operating system is not going to give access to its process to all memory. Instead, it's going to just take a chunk of main memory and give it to the process. And the process is not going to be able to access memory outside that little chunk. So here's a more pictorial representation. This is what we call physical memory. This is basically the contents of main memory, and we call it physical because this is what's actually stored in hardware. And then different processes are going to have different regions of physical memory allocated different regions of physical memory allocated for them. And so, for example, the operating system kernel is going to take some memory here. Process 1 is going to have this range of addresses, and so on. So this is what we call physical memory, but at the same time, let's think about what each process sees. So for example, what process 1 is seeing is what we call virtual memory. For process 1, the address space begins here, right? So address 0 begins at this point in physical memory, and then there's some chunk of addresses that it has allocated. So address 0 is here in its own virtual private address space, but it actually maps to somewhere in the middle of physical memory. And so we'll see that this requires a little bit of hardware to do this translation between virtual and physical memory. And then the process cannot go and access some address over here. It's going to have, let's say that it has 1 megabyte allocated. So it will be able to access every address between 0 and 1 megabyte. But if it tries to access something below 1 megabyte, the 1 megabyte region, the operating system will step in and say, no, that's an illegal memory address. You cannot access that, right? And so this is what essentially is going to let us have processes that are isolated, right? They don't actually see each other's memory. They don't see each other's data. Okay, the second key function of the operating system kernel is scheduling processes into the CPU. So the RISC-V processor that you've been building is a single CPU. If you look at your laptop, you probably have multiple CPUs or multiple CPU cores. So you can run multiple processes at the same time. But in general, you're going to have in your machine many, many more processes than you have available CPUs. And let's just take a look. I am logged into one of the Athena machines here. You can, this depends on your operating system, but for example, you can run top in any Linux machine. And it will tell you here the tasks, right? So you can see that, well, Linux or top calls these tasks. These are actually processes. You can see that this machine is running over 1,000 processes has over 1,000 processes running. Actually, most of these are sleeping. Between 1 and 3 are running at any given time. Others are waiting for some event to happen. For example, if you have a text editor open, it's just probably waiting for user input and not doing any processing right now. You can also see more details on the processes that are actually running, right? So you can get a list of what command does each process correspond to. But I, as an user, cannot go into some of these other users' processes and read their data because they're in separate parts of physical memory. Now, when we have so many processes, we will get into a situation where we have more things to run than we have CPUs. And so what the operating system is going to do is it's going to give some fraction of the CPU time to its process, right? And so it's going to schedule a process for some amount of time, let's say a few tens of milliseconds, and then it will step in, take this process out of the CPU and give the CPU to another process, let's say process 2. After some time, it will again step in and swap the processes again. So both of these processes are running on the same CPU, just at different points in time. And to these processes, and this is something really important, these processes actually believe that they have the whole CPU. Right? You don't need to do anything special when you write a program to yield the CPU or say, let me count until I have used my 20 milliseconds worth of quota. No, you write it like you have the whole machine. And then if the operating system needs to interrupt this process and give the CPU to some other process, it will do that for you. Right? So we have private address spaces, we have scheduling, and the third major component of operating systems is essentially providing services to applications. And this is done through system calls, which we will see in a few slides. This is essentially everything that the operating system is abstracting, things like files, like network sockets, which is how you interface with a network card and send messages over the network, events, all sorts of functionality that the OS provides to make it easier to write applications. Okay, so if you think about what these mechanisms are, when considered together, we can think of this private address space as a virtual memory that is a memory that is not actually physically implemented. It doesn't exist in practice. This virtual memory maps to some fraction of physical memory, but there isn't a separate physical device that is just dedicated for this memory. And likewise, this CPU is now a virtual CPU. It's not really a CPU that's dedicated to a single process, but it's shared among multiple processes. And so if you consider all of these, what you have is a situation where each process believes that it's running in its own machine. Right? You write the application like it's running alone in the system, but actually it's not. Actually, the operating system is giving the illusion to its process that it has its own machine, that it has its own CPU, that it has its own memory, that it has its own files, that it has its own events, display, and what have you. But this is a lie. This is an emulation. Right? What the operating system is doing is multiplexing multiple of these processes over hardware, and the abstraction here is what we call a virtual machine. So let's see how this works in a little bit more detail. We have physical hardware at the bottom, right? We have the physical processor, memory, all these I/O devices. Then the operating system kernel, this specially privileged process, is directly talking to this hardware, and it is providing a virtual machine to each of these processes, right? It is providing this ABI, this interface between the operating system kernel and its process, essentially consists of a virtual processor, a virtual memory, and all of these other facilities that are implemented through system calls and other ways of communicating with the operating system, right? So if you look at it from the view of the process, right, all the process sees is this interface, and all the process believes is that it's running alone in the system, right? But in fact, the operating system provides a different virtual machine for each different process, right? So you can have processes 2, 3, and 4 here with their own virtual machines. Now, virtual machines are a very general concept, so we'll spend a few minutes looking at all the different places where they arise. But generally, we say that a virtual machine is an emulation of a computer system. So what do I mean by that? Every time that you have a process, right, that believes it is running on some machine, but you don't actually have a physical machine implementing that machine. Instead, there's another process underneath that's actually implementing some of that functionality. You have a virtual machine. And this happens in operating systems, but it also happens in many other places in computer science. So you might have heard about the Java virtual machine or the Python virtual machine. Those are language level virtual machines. You might have heard about VirtualBox or VMware. Those are system level virtual machines. And so let's take a look at where these virtual machines arise by just looking at one concrete example. And so without looking at the handout, can you tell me how many virtual machines did you use in Lab 2? Let's count. Okay, so in Lab 2, you wrote a program called Quicksort. Yes? This is a RISC-V program, and when you run it, it's a RISC-V process. And this process is coded against the RISC-V ISA. Right? You wrote assembly, and it was running RISC-V instructions. But we didn't give you a RISC-V processor to test your machine, your program, right? Instead, what we gave you is another program. We gave you a Python program that emulates a RISC-V machine. Yes? So that is a virtual machine. We gave you a RISC-V emulator that implements a RISC-V virtual machine. And in and of itself, that is another process, right? That's another program that's running and looking at the instructions and decoding them and interpreting them and setting up some memory. And you can go and take a look at the code for the simulator. It's just a normal Python program. Okay, so we have this RISC-V emulator. But this RISC-V emulator being a Python program means that this is not actually assembly instructions. We don't compile Python programs down to assembly. Instead, this is coded against the Python language. And there is another program underneath that is the Python interpreter that loads this Python file, interprets it, and runs it. Right? So this Python interpreter is yet another virtual machine that's implementing a Python virtual machine. This is written in C and it's compiled down to assembly, so it actually does talk with the operating system directly. In particular, in Lab 2, we're using Athena, so those are Linux machines. And so this is coded against the Linux application binary interface. So underneath, we have the Linux operating system kernel. And this Linux operating system kernel is implementing a Linux x86 process level virtual machine. Right? It is giving system calls. It is giving all of the facilities that we've seen so far in this lecture to this Python interpreter. Files, I/O, and so on. Good? Okay. Now, as I mentioned before, this is coded against the x86 ISA. This runs on an x86 machine. x86 is the most widely used instruction set architecture. So this could talk to hardware, right? And you really couldn't be faulted for thinking that the next box that I'm going to show you is some physical hardware. However, it's not. And so let's actually take a look. If you actually go to this Athena machine and start listing what hardware looks like, you'll see that it's actually quite a weird machine. For one, it has 23 gigabytes of main memory, which, all main memory sticks come in powers of 2 sizes. So if you get a prime number of gigabytes, you should start suspecting that something's off. And, there are some processor cores. But then when you scroll down, you start seeing all these devices that have this weird manufacturer, VMware. And so, there's a VGA, there's a display here that's manufactured by VMware, and a PCI bridge that's manufactured by VMware, and drives that are manufactured by VMware. Now, VMware is not some, super large company that's building, entire systems and building full pieces of hardware. No. VMware is a virtualization technology company that implements a virtual machine. And so it just gives you a process that emulates a system. So this is emulating an x86 system. And there are very good reasons for ISMT to use VMware here. For example, they can move these virtual machines, the system-level virtual machines, across different physical machines. They can migrate them, they can pause them, just like you can pause a process, right? Or they can share multiple, Athena machines might actually be sharing the same hardware. So the point is that there's a virtual machine below, and what this means is that, for example, when this Linux kernel writes to a disk, it believes that it's actually writing to a disk, but this process below actually implements the disk as a file. So you have translation going the other way around, where this is a file in some other system somewhere else. Finally, this is yet another process, right, that is talking with some operating system. I really don't know what ISMT is using. Probably FreeBSD, probably Linux, hopefully not Windows, although Windows would explain some things. But you'll have whatever kernel this is running against. You have another operating system kernel below, and finally, and I really hope this is the case, this again is talking x86 ISA, and finally you'll have hardware. Although I honestly don't know. Maybe there's yet another 3 levels of virtual machines below, and there's some server in Finland is actually running all your Athena machines. I don't know. I haven't asked. So the point is that if we go and count, right, we have 1, 2, 3, 4, 5 virtual machines that are involved in running our RISC-V program. And so that's quite a lot, right? Now, not all of these are the same or at the same level of abstraction. Broadly speaking, we talk about 3 different kinds of virtual machines. On the one hand, we have system-level virtual machines, and those are the ones that implement an ISA, right? So we have this x86 ISA and this RISC-V ISA. Those are system virtual machines. We have operating system or process level virtual machines. Those are what implement the ABI. So we have 2 of those here. And finally, we also have a language level virtual machine that's much more abstracted, right? It's implementing things like classes, and it's abstracting memory in objects, and it's doing many more things that do not quite correspond to hardware. Yes?
Why do we have to call something a virtual machine as opposed to like a program that feeds one into another?
So that's a great question, and the distinction is actually very clean. When you're running a process, and there's another process that's indeed taking care of running that process, the litmus test there is that you shouldn't actually be able to distinguish between the physical machine and the virtual machine. For example, if I went and implemented a Python hardware interpreter, right, I could actually give you some machine that runs this Python program. It would be a fairly complicated one, so we don't do that. But the difference between that and 2 other processes that are communicating is that you're actually aware that you're communicating with some other process, right? It's like, you have a queue or you have something that's very explicit versus you're in the matrix and you don't know whether you're actually being emulated or not, right? That's basically the difference. Okay, so we want to implement virtual machines, right? Because these are a very, very pervasive concept. But if you do this in software, it's actually really expensive, right? So think of Python. In Python, it's common that if you write Python programs, that they will be 10 to 100 times slower than an equivalent C program that does the same computation. And that is because you have this Python interpreter running underneath and essentially doing in software what, using a lot of instructions, what actually takes 1 or a few instructions in hardware, right? And so if you write it in C, it's just going to take fewer operations to do the same thing. So because we want to support operating systems with minimal overheads, there's a little bit of hardware that we need to add to our machines for the system to be efficient. So we're going to have, broadly speaking, 4 kinds of ISA extensions. We're going to change the ISA in the following ways. First, we're going to add an extra mode of operation, an extra mode of execution that we call Supervisor Mode. So we're going to have User Mode and Supervisor Mode. The operating system kernel is going to run in Supervisor Mode, and all other processes, all normal processes are going to run in user mode. And the key thing here is that in supervisor mode, we're going to have access to special capabilities. Right? The operating system kernel is going to be able to do things, because it's in supervisor mode, that normal processes cannot. And specifically, the things that it's going to be able to do are A, we're going to have privileged instructions and registers, or privileged instructions and privileged state, that are only available in supervisor mode. And then, the question is, well, we have these two modes, user and supervisor. We need some way to transition between user and supervisor mode. And that transition needs to be very, very, very carefully orchestrated. Because if you have a normal program and you let that program just flip the user bit into, or the bit that determines whether you're in user mode or supervisor mode, then why are we introducing the supervisor mode, right? If anybody can claim to be the operating system kernel, right? So we're going to have to design that interface so that we cannot have programs themselves arbitrarily say, hey, I am the OS kernel now. Give me access to all the resources. Finally, the last piece of the puzzle is we're going to have virtual memory. We're going to have some hardware to divide this physical memory into multiple private address spaces. So today, we're going to see the first 3 mechanisms, and in the next lecture, we're going to see virtual memory. But at a high level, the only thing you need to understand about virtual memory is this, that there's some translation process that its process is unaware of, but that it is under the control of the operating system. Now, in the rest of this lecture, we're going to focus on concepts and discuss things at a very high level. In fact, I don't even want to talk about RISC-V until the last 2 slides. And what we're going to do is the recitation tomorrow is a special recitation. So instead of just instead of having normal problems like we would ask you on the quiz, we've prepared a little demo. So we have a tiny operating system that's just a couple hundred lines of code, and you'll see and do a few changes to that tiny operating system in recitation tomorrow. But so today we're going to focus on seeing the concepts that you're going to see very, very concretely tomorrow. And the high-level point here is that for these things to work, the operating system and hardware need to be completely in sync. Right? If you start having some mismatches as to how these resources get used, lots of bad things can happen. Okay, so the key concept that I want to start with is with this exception, right? With this mechanism for transitioning from user mode to supervisor mode. And so an exception, as the name implies, is some exceptional event. It's something that happens rarely. It's something that is unexpected. This could be because the program is doing something that it shouldn't be doing, or the program has a bug, but also because there might be some device that requires our attention, right? So, there's some program, right? Some sequence of instructions are running from this process, and at some point, either the process does something in this instruction that's not okay, or there's some event that the operating system needs to handle. And so what's going to happen is that we're going to transfer control from this instruction. We're going to stop the execution of the process right here. We're going to transfer control to some other code, that's the exception handler that's within the operating system kernel, that is going to handle the event, and then it will return control to the process. So, if this is some external event, we return control to this instruction because this instruction had nothing to do with the event that we needed to handle. Sometimes this instruction will do something that is not correct, but the operating system will sort of fix things and either go back to this instruction or go back to the next instruction. And we'll see examples of the different things, the different causes for these exceptions. And in some cases, the exception handler will run and say, you know what, that's just wrong. Like, you're trying to access a memory address that's illegal, and so I'm just going to abort the program. And so, the exception handler might run and then just decide to not return to the process and to terminate the process. Okay, so the terminology for exceptions is a little bit confusing because there are 2 terms that are used interchangeably or almost interchangeably. They're called exceptions and interrupts. And there's a minor distinction between them. The distinction is that when we talk about exceptions, generally we refer to events that are synchronous. What I mean by that is there are events that are generated by the process itself. The process runs an instruction that generates some exceptional condition that the operating system needs to step in to handle. Things like, it's trying to execute an instruction that's illegal. Right? Now in Lab 6, you've seen, or you are seeing, that there are a lot of opcodes and a lot of instructions for which you need to say the type for this instruction is unsupported, and what the operating system would step in on all of those. But things also like if you had a divider, if you divide by 0, that is also an illegal operation. Maybe you're trying to access some memory, process 1 is trying to access some memory below where it should be, right? And so the operating system should also step in. So in all of those cases, we call these exceptions. And then interrupts, we usually refer to them as asynchronous events. That is, events that are generated by I/O devices, by the disk or the keyboard. You press a key in the keyboard, and that generates an interrupt that stops the current process and gets the operating system to run. Now, in this course, we're going to use exception to talk about both kinds of events, and then we'll use synchronous exception for synchronous events. And when we talk about interrupts, those are the asynchronous events. But you'll see completely different, like some people actually use the complete opposite. This is essentially a RISC-V nomenclature. So what are the things that we need to do in our hardware to handle exceptions? Right? There's a little bit of a dance that we need to do between hardware and software. And one conceptual issue here is that there's a process that's running in the CPU. There's some event that happens, right? And then we need to use the CPU to handle that event. So the operating system is going to step in and take the resources take the CPU that the process has. So you can think of this as kind of like a procedure call, except it's a call that may happen everywhere on any instruction at any point in the execution of the program, but it is a control transfer. And so it is not that different when you look down at the mechanics from a jump or a branch, except we need to do a few more things. So first of all, we have what we call precise exceptions. And so this means that if you have at a particular instruction an exception happens, then that instruction cannot have any effect on the state of the system, but the processor will guarantee that all the previous instructions have been completed, and also that none of the later instructions have had any effect, right? It will essentially stop the program precisely at that instruction. And this is kind of obvious with the processor you've seen so far, because we've only seen processors that execute one instruction at a time. In a few lectures, we'll start looking at pipelining, and so we'll see that we actually want to overlap the execution of multiple instructions. Modern processors run about 100 instructions concurrently, and so this precise exception mechanism is trivial for the processor you're building or you've built, but it's not that easy in more complex processors. Then we need to implement this control transfer, right? So because we're transferring control, just like with jump and link, you need the link part, right? You need to figure out where you were. You need to tell the operating system, I had an interrupt or an exception on this particular PC. So you need to save the PC in a special register. And also we're going to save some other information that tells us why did this exception happen, right? Was it an illegal instruction? Was it an illegal memory access? Was it some other thing? And those we save in registers, but we save in registers that are privileged, that the process does not have access to. And finally, in one shot, atomically, the processor is going to do the following. It's going to put the program or the hardware in supervisor mode. So it's going to enable supervisor mode. It's going to also disable interrupts so that the operating system can handle, or the exception handler can handle, this one particular interrupt without being interrupted itself again. And then it is finally going to do the control transfer. It's going to set the PC to a pre-specified PC that the OS has given it, that is the start of the exception handler. So now this exception handler is going to run, and if it can handle whatever exceptional condition it was dealing with, it will just return control to the process at the instruction that it was. So the process just doesn't see anything, right? The exception is just completely transparent to the process. On the other hand, if the exception is due to something that the operating system cannot fix, so for example, the process is trying to do some illegal operation, like an illegal memory access, then the operating system will just abort the process. Okay, so we're going to see 3 different use cases for exceptions. The first case and the second case are directly involved in creating this virtual CPU, in virtualizing the CPU. And so the first functionality here, the first use is CPU scheduling. So remember, one of the key functionalities of the operating system is that we need to time multiplex each CPU across multiple processes, right? So each process is going to take a fraction of the CPU time, and it cannot take more than it should. So the key enabling technology that lets us do this very reliably is timers. So a timer is just a hardware device. You can think of this as a counter that will at some point reach a threshold, and when it reaches a threshold, it will just interrupt the processor. So the operating system can configure this timer to say, please interrupt, please raise an interrupt in 10 milliseconds or 20 milliseconds, some pre-specified amount of time. And using that, the operating system can now go ahead and schedule multiple processes over time. So let's see how this happens. So initially, you have the kernel. It's running it's running on the CPU, and at some point, the kernel decides that it wants to give the CPU to some user process. So what it does is it sets the timer to fire at some future time. In this case, it sets a timeout of 20 milliseconds. So now we're at millisecond 10. At 30 milliseconds, we'll get a timer interrupt. Then it loads all the state. It loads the registers. It loads the program counter. It loads some other privileged registers that have to do with virtual memory, which we'll see next lecture, for process 1. And then it just returns control to the PC of process 1. Right? Just let's process 1 run. So process 1 will run on the CPU directly, right? Now process 1 is just running instructions, and it's just as fast as if process 1 had complete access to the full machine for that time slice. Except at time equals 30 milliseconds, the timer will say interrupt. And then the exception handler will run. And the exception handler will say, okay, your time's up. We'll save all the state of process 1. We'll choose some other process to schedule, let's say process 2, and we'll repeat the same process. It will load all the state in, it will let it run. Let's say, in this case, it decides to give process 2 30 milliseconds instead of 20 milliseconds because process 2 may be higher priority or it needs more resources, right? So it can allocate the CPU with unequal priorities. And this repeats over time, and so you can see that each process is believing that it has its own CPU when in fact, no. They're only using the physical CPU for a fraction of the time. Okay, any questions so far? Good. All right, so the next use for exceptions is to emulate instructions, to emulate hardware that we do not have. Let's just look at a very concrete example. So RISC-V has many variants, many ISA variants, and what you've implemented is what we call RV32I, which is the most basic subset of the instruction set. And one instruction that we do not have, but there's an extension called the M extension of RISC-V that extension introduces this multiply operation. M stands for multiply, and multiply essentially just multiplies x2 times x3, multiplies both the contents of both registers, and then stores the result in some other register. But because our ALU doesn't have a multiplier, we don't have that implemented. And so in your processor, this will cause an illegal instruction exception. Right? So this will invoke the exception handler. Now, you could have an exception handler that says, this is an illegal operation, abort the process. It's trying to run something I don't understand. But the exception handler can also just go ahead and emulate the instruction, right? It can say, that's a multiply. Now, I don't have a multiplier, which is why I got an exception here, but it can actually go and perform a multiplication with simpler instructions and then return control back to the process. right? So specifically, this is what happens. Process 1 is running here, right? It has an add instruction, a multiply instruction. This instruction, the processor wants to run this instruction, and then it figures out that it is an illegal opcode. So it raises an illegal instruction exception, and the kernel steps in. Now the kernel does a few things. It saves the state of process 1 so that the kernel itself can run, and then it figures out, oh, this illegal instruction, I actually understand it. It is a multiply. And so let me call this multiply routine in the kernel that's multiplication by repeated addition. Now I'm going to save the result in register A4. I'm going to load that in process, load that state again back in normal registers, and then return control at the next instruction. Right? So transparently, now the process 1 believes that it just ran a multiply instruction. It didn't. It called into the operating system, which executed a multiply using other instructions for the process, right? Okay, any questions? So the result is that the program believes it's running in a processor that has a multiplier when the processor actually does not have a multiplier. In a sense, we're virtualizing the processor, right? We're making it look like the processor has capabilities that it doesn't have. And that's why we talk about a virtual CPU. Okay, is there any problem with this approach? Why do we implement processors with multipliers after all, if we can do this? Because we do have processors with hardware multipliers. Yes?
Implementing a multiplication, like emulating instructions, is much slower than having it done in hardware.
Exactly. This is much slower. In fact, it is also much slower than calling a subroutine in software. Right? So if this program called a multiply subroutine, it will also be faster. So this is not the best abstraction in terms of performance, but it does let the kernel emulate things that hardware does not have. Okay, the last use of exceptions is to implement system calls. So remember, we have this virtual CPU, and that's the two first uses of exceptions. We have virtual memory, which we'll see next lecture. And then we have all these other facilities that essentially let us talk with I/O devices, right? Things like print things to the screen, save or load and read and write files, and so on. And here, we're going to reuse the same mechanisms for exceptions, but in this case, it's not like the application is doing something that it mistakenly triggers an exception. In fact, what we have is a special instruction that causes an exception when it is invoked, whose whole purpose is to cause an exception. This instruction is called eCall for environment call in RISC-V. You'll see this in lab tomorrow. Other ISAs call this system call. Other ISAs just have an interrupt, an instruction called interrupt. So this varies a lot by ISA, but the key takeaway point here is that regardless of the ISA, you reuse the same mechanism for exceptions to just have the process tell the OS, I need help. I need you to do something for me. Please take over and do whatever I'm asking you to. So there are many system calls in Linux. The main ones are, for example, for accessing files, using network connections, managing memory. So for example, you can allocate more memory here. You can give up some of your existing memory. You can ask things like, what is the time? What is the current time? What is my current ID? What's the user who's running this application? You can wait for certain events, and so on. You can create other processes, and so on and so forth. Two important points here are, first of all, you're rarely going to use this directly. These are implemented by the operating system, but then there's a library, an extra layer in the process itself, where you have the language library is the thing that's calling these system calls, and you are calling functions that also abstract this a little bit. And also, the other point that I want to make is that some of these calls might block the process. For example, some of these calls are, I want to sleep for 3 seconds because I'm waiting for something to happen. Or I want to wait until the user types something into gives me some input, right? Or I want to read some file, and unfortunately, that file is on disk, and the disk is busy, and it's going to be 50 milliseconds until I can actually get the data. So the operating system is going to have to pause or block that process. And so if we look at the lifetime of a process, just adding this notion of system calls may block the process, what we see is that a process is initially created by some other process, because processes can create other processes, and initially it is ready to be executed, but it is not yet running. At some point, the operating system kernel decides to schedule it, and so it is executing. It is now in the processor, it is actually running instructions, and after some time or interrupt, it will be descheduled and it will go back to ready. Now, if the program reaches its end, it will exit through a system call, and it will be done. It won't exist anymore. But there's another condition where if the program wants to invoke some operating system service that requires it to wait for some other event to happen, it will go blocked, it will go into this waiting state. I will stay there until the operating system figures out that it doesn't need to wait anymore. For example, the time for which it wanted to sleep has elapsed, and then it will be woken up and go back to ready. And so the operating system is maintaining the state of all these different processes, right? And it's only scheduling ready processes, and it just has a pile of waiting processes that are waiting for something else to happen. Okay, how exceptions happen in RISC-V? We're not going to go into the details in this lecture. As I mentioned, there's several privileged registers, which we call CSRs. There are privileged instructions to access those registers, and there's the equal instruction for system calls. And you'll see all of this in detail tomorrow in recitation, which will be a demo of a tiny RISC-V operating system. All right, that's it for today. Thank you.